All right, so good morning, everybody. Welcome back to day 2 of our weekend hackathon. Get all these notebooks out of the way. Just have a very quick intro and reminder of schedule, then we'll do our morning check-ins and let you all get to work. So just as a reminder, this session, this welcome session is being recorded and live streamed, as well as the check-ins. We'll stop recording once everybody moves to the breakout rooms. There's no point in recording and live streaming dead air. But we will be recording and live streaming the check-ins and group discussions today. So do keep that in mind. Again, you can find any of the hackathon materials you need in the hackathon folder below. And that's about it. I think everybody's in the Slack at this point. So just a quick reminder of the schedule for day 2. We're going to spend the first half hour or so checking in with the group, find out if anything happened overnight. We didn't have our official check-in last night because we kind of heard from everybody a little later in the day as it was. So we'll kind of treat this morning as our catch up from not checking in last night. You'll have from 10:30 to 2 to work on models. We'll do another quick check-in from 2 to 2:30. Find out what everybody needs for their final help for the day. We'll also give you the template for the reports of discussion at the end of the day at that point, to give you a little bit of time to put together just a couple of slides on your presentation or on your project. And then from 2:30 to 5, you'll have some more work time. And then from 5 to 6, we'll do reports of discussion. And conclude for the day. So very quickly, start with check-ins. So just 4 quick questions. Any progress overnight? What is the current state of your model? If you would like to show us the model running, that's fine. Again, we're going to try not to use this check-in as too much of a debugging session this morning so people can get off to work. But we would like to see, if you do have your model running, what it currently looks like. Give us your plans for today, like where you want the model to be by the end of today, and what help you need from us. We don't have the breakout rooms open yet. I think we'll have to rebuild them actually, because this is a new meeting. Let's start with the cell ECM group, if I remember properly. Probably here, actually.
Well, I was in that group, but I don't know if they're here. They mentioned that they would come back a little bit later today or something. There's a very interesting question that we can discuss later, James. We were trying to use a field and a way to control the contact energy between cells and the medium based on this gradient of this field, right? So it sticks more to the medium if the concentration of this field is higher. But the problem is when you change a molecule or how the molecule is interacting, or the density in the medium, you change for everywhere, not really on the space where the cell is, right? So we were trying to find a way on that. And I'm playing with some toys here on my side, see if I can figure it out.
You could change the cell's motility instead of its adhesions.
That's a good point. Yeah, I can change the motility instead of adhesion.
Or you change the density of integrins on the cell.
I think we have a few ideas of where our model went wrong, and there's a few things that we want to try first. But yeah, I think we're close as well.
That's fine. Check-in it's fine to say that you want to talk later. I mean, it's just an opportunity to try to make sure that if you need help, that we can provide it, and especially if there could be collective intelligence from all the people in the room as opposed to just 1 or 2 instructors helping out. So thanks. That's just fine. No worries.
Thank you.
Thank you. Because of the time zone as well, like after the session yesterday, we are just working in the morning today, and there's not a lot of time that we can work. But yeah.
Okay, so the liver group.
We still need a little bit more time to work on our stuff. We don't have much more to report for now, I guess.
Okay, that's fine. Any specific help that you need from us today?
I'll let you guys know.
All right, sounds good. Let's see, evolution. How are you doing today?
Hi. So as you know, yesterday at the very end of the day, we had a long discussion, deep dive about adhesion flex. And I then went off and thought about it some more, worked on it some more, did some refining of a sorting simulation and got much better control over it. So I think I'm doing well. But of course, I don't want a sorting simulation. So I'm now working on a different setup with cells individually wandering around, and it's not quite right. So I have a little work to do, Maria. I'll catch you up when we get together, and we will get that working. I may need for what I want 2 different cell adhesion molecules, one for attraction and one for repulsion, that get played off of each other. So that's going to make it more complicated, but we'll see what I can do with just one molecule first. And then we'll be off. And the other thing is at 1:30, I need to disappear to do a very short family thing for about half an hour. And I know we have I think our thing is at 2 o'clock check-ins. I will be back for that.
Okay, that's good. Julio, it's Father's Day, I think. Father's Day here was last month. So yes, Julio, take a break today to spend some time with your dad. If it's Father's Day there. But all right, Marcella.
All right, so what I'm doing is stupidly simple since it's just me and I'm new to Python and CompuCell3D. So what I did so far was like I have a complicated ODE model of macrophage differentiation in the inflammatory response. And I'm trying to break it down into submodels that are digestible, that I can build piece by piece. And what I've accomplished so far is I have, well, can I share my screen super quick? I'm not going to do like a whole presentation. I just want to show you. I am putting together a PowerPoint. I'm not going to go through the whole thing, but I'm just going to show, it gives the summary that what I did was I built a very simple antimony ODE model that has just macrophages. They die, they proliferate, they transition from one phenotype to another. I did that in the familiar way for me is to do it obviously by writing ordinary differential equations. I'm new to writing it in this format with the rate equation, so I'm proud of myself for being able to do that. And then I tried to create something that could reproduce this very simple behavior using CompuCell3D. So the cells in there also just grow and die and transition. And right now it's all random. I don't have anything driving it because there's no inflammatory stimulus, there's no cytokines, there's nothing. So I just have it programmed in there as random events just so that I could get the framework set up. And I'm proud of myself that I was able to do the shared dictionary so that I could track all of this happening. It's all very simple and basic, but I at least have a framework now. that I can build on, I think, because that is really the rationale, right? The purpose here, I'm not doing antimony because I'm going to have subcellular things going on that are then going to map onto the cells. I'm creating this model in antimony just so I can kind of verify that it's behaving similarly to, okay. And then the next thing I need to do is start thinking about actual behaviors that I want. And I guess the first place that I was going to start was just adding cytokine expression in the ODE model, and then doing the same in CompuCell 3D.
That's impressive. Fantastic. If you want
you.
somebody to help out, and you want a working group, a breakout room, just let us know and we'll set it up for you.
Okay.
Definitely create a breakout room for her. Eventually, someone will go there and help her. Even if it's me.
Okay, that'd be great. Yeah, I'm also going to be, so I have grandparents coming and kids and all that. And so I also have family stuff, but I'm going to be coming in and out and working, which is how I just work all the time anyway, in bites of 15 to 30 minutes. So I'll be doing that. But as far as the cytokine expression goes in CompuCell 3D, and this is totally new to me, that I actually can have the cells like secretion. I think we did that in a module. I need to go back and check which module it was so I can reference it. But I'm going to have the cells secrete the cytokines. And then, yeah, I just need to go back and relearn how that's handled. So that's my next step. All right, well, thank you. Let's stop sharing.
Great. And Cesar, I think that's, I think we covered all the groups after Cesar goes.
Hello.
Oh yeah, Julia, sorry. How can I forget
Here
Julia?
Good morning, and I have to say that Pedro encouraged me a lot yesterday to give up the fibers and start doing something more like ion tracks in materials and creating semiconductor foams, like I said my project was. And I have actually something to show already, but okay. You know, like I said yesterday, the objective, the final purpose is to simulate this material. It's, you know, how can I say this? It's rotated 90 degrees, but you can imagine here a material, a bulk material, you know, a slab of material, and the ions come from the right to the left, and they start to reorganize the material, creating bubbles, and then it resolidificates, reorganizes, and stands like this after the process stop. And you know, in some cases it becomes like this with even more fluency. Okay, but then what have I done? There are two versions already of the program. And this is one. I have to say, it's like this. I made a graph to keep track of the volume and the surface, to see the surface growing with bubbles while the volume keeps constant. And the one way me and Pedro thought to do it was just one big cell of material and bubbles being created in randomly, not actually, okay, but in a line every amount of Monte Carlo steps, and then it starts to create. Okay, it's frozen. Okay, as you can see, bubble is being created here. Like it's not a classical process, you must know that. It's not like a hot tunnel and everything inside melts. It's like there's a chance of the ion interacting with the material and creating a gas bubble of the material, and then it stays there as long as nothing else changes. And this was one of the biggest problem. The material, the volume keeps growing everywhere, not just where it was hot, you know. And then another bubble grows, and then another bubble grows, and you see the green keeps growing bubbles. And then I have tried keeping the gas, but it started taking a shape that was like half of the material was gas and half was solid. And this is one of the ways to do it. It's not very, you know, accurate with what happens in reality, I think, not for now, but at least the volume keeps constant and the surface keeps growing. And you can see that it really grows. It's not fake news. And the other one I'd like to show is this one. This one I took the idea of not going to medium. The gas do not turns medium after a while. It turns pour. So it could have different lambda and target volumes as I want, or surface or something. And this was like the result after many Monte Carlo steps. And you can see the shape is not real like this, but it's kinda, you know. There are pores and they interact with volume changes, but at least they are not like vanishing like when it was with medium, like here. Because in this way, like it was like if the solid was always hot and melting. And you know, it's not like this, it's more local. One way to do a more local volume change would be, I think, creating more solid cells and interacting just by the neighbors or something like that. But it will be in another grade of difficulty, I think. So these are the two versions that I have already. Let me stop. I hope everyone was listening. I wasn't seeing anything. Yeah.
The image that you're showing, your real world image, that sure looks a lot like the cell boundaries in a soap bubble.
So boundaries, I had put it like no flux.
But I think, no, I'm saying is if you make a dense pack 3D cell field and go through and convert every pixel that is actually a contact pixel between two cells, you convert every pixel into another cell type and then get rid of your cells, you'll have that porous image that you're showing. So if you show that 3D fiber image you had.
This one. This one?
You can hit share again.
Oh yes.
James, doesn't this look like a bubble coarsening?
Yeah, it is. It's a solid.
Boundary.
It's a open solid foam.
Yeah, and it's the boundary between cells. It looks very similar to the boundary.
Yeah. These ones are solid foams, and this one is a semiconductor foam created by ion irradiation.
So that's one way of doing it is like you were doing But instead of starting with a solid mass and introducing a small number of bubbles, start with a solid mass of cells. And then if you just make the negative space, basically, like I say, you iterate over every cell's surface pixels and convert them into another cell type, you'll get that kind of spongy bone network formed.
Yeah, I believe so, but then I will be not conserving volume, I think, or not.
Well, you're conserving, you know, your gaps there, you're just going to fill with a cell. And you really, I wouldn't worry too much about conserving volume at this point as trying to get that layout. The other thing is that upper image almost looks like the diamond lattice. Yeah, I don't think we've ever tried to do anything like a diamond lattice in CompuCell. That lattice you're showing looks exactly like the lattice of blood vessels in the liver. And those voids would be one cell inside each one of those voids, and all those lines would be blood vessels. But if you kind of squint your eye and look at that for a minute, you'd say that, you know, that's the diamond lattice. You've got every vertex looks like it has 4 connections.
Yeah, and you must know that this is like one of the possibilities after irradiating for a long time, like with many ions interacting with it. It's like the number of ions. There's a I don't know the words. There's a quantity in ion irradiation that is fluency, and fluency is like ions per squared centimeter, and you can see like it's a lot of ions. And when the fluency is low, it starts with small bubbles, and then if you irradiate a lot, it becomes larger bubbles. But not every material becomes like this.
Yeah.
I think looking to get this is like maybe contaminates the initial idea of creating bubbles. I don't know.
Well, so your upper image, your nice semi-tetrahedral lattice image, you would get that if all your cells are the same size and all were, you know, they're not spheres, they're you know, whatever the hell they are, truncated hexagons or something like that. If those cells that create that network there, so the edges you see there are the boundaries between more than 2 cells. And you don't get very many faces because you don't have a lot of face interaction if the cells are all the same size, or you don't get as much. But if you start to elongate the cells, your edges will start to turn into sheets, right? If your cell starts to stretch this way, now you get a long sheet where 2 long cells are adjacent to each other. So I wonder if that would be a way to go from that starting image to your images where it's more of a sheet and less of a network of pipes. Is that the right direction? You want to go from this image to the sheet image, or is it the other way around?
Maybe it's a possibility. And there is another big problem that I think I won't be covering in this hackathon, that it's not every material that becomes porous. It's like indium antimonide, gallium antimonide, like germanium, and some other elements that really start becoming foams. The other ones just doesn't do anything. They just melt and becomes solid again with the same structure.